Hey guys, so this is the lesson that I was told introduces new by Mr. Morrison, is where the new things get introduced to this section here on vector dynamics. The incline plane. If we look at what's going on here, we've got a person on a ramp standing on a Newton scale and attached to a rope. We want to look at as the angle increases, what happens to the scale reading. So I would like you for a second to, well, this is where this problem comes from. If you ignore all the rest of the page, this looks like a person standing on a flat scale with a rope attached to them. Now, we know that the normal force goes upwards from, or perpendicular from the ground. So I'm going to draw that in here on this very flat looking surface. So our normal force is going up that way. Perpendicular to the ground. Now, as we look at what's going on here, we don't actually have that flat situation. We've got an angled one. We've got a ramp angle here, and it's going to start to increase. Now, what's actually going to happen to the scale is what we want to find out. So let's take a look at what's going on here. Again, if this was the situation, Fn would be perpendicular to the ground, and gravity would be straight down. Now, as we angle this thing up, Fn remains perpendicular to the surface, but gravity also has to remain straight down. So we have a situation that looks like this, where gravity is straight down and Fn is up on some angle. Now, what's actually happening here? What do I equate Fn to? And this is where we're going to bring in components. So as this angle here increases, we have to break gravity up into its two components. This angle here is 90 degrees. I want to make a note here. Components always meet at 90 degrees. So it's the components that have to meet at 90 degrees. And so what we've got here are the two components of gravity. I'm going to call this one Fg, and I use these two lines to represent parallel, because this Fg is parallel to my slope, and I'm going to call this guy here Fg, and that's the symbol for perpendicular. Now take a look at what's happening here. As if this thing were level, Fg perpendicular and Fg would be the exact same thing. As this angle increases, this angle in here also starts to increase. So these two angles that I've drawn in here, and I can prove this to you a whole bunch of different ways if you want to look at the geometry of it. These two angles here, I'll label that guy theta and this guy theta. I'll labeling them the same because they are the same angle. And again, if you want proof, I can prove that to you a couple different ways later. Or you can take my kind of hand wavy argument. If you look at what's happening here, as you crank up the ramp, you're going to start to create, this is going to start to get larger and larger and larger and larger and larger, because Fg is going to remain straight down. So what's happening here, we've got an Fg straight down, we've got Fn perpendicular to the ramp. We've got a component of gravity. It's also perpendicular to the ramp. So if we look at what's going on here, we can see that Fg perpendicular is going to be what is going to end up being equal to Fn. And we know that if this is in a triangle like this, this is the 90, this is the hypotenuse. The hypotenuse is always the longest side. So if Fg perpendicular is equal to Fn, and Fg perpendicular is less than Fg, we know that Fn has to be less than FG. And if the scale measures FN, and it's now less than FG, the reading in the scale has decreased. You can argue it that way relatively easily, I think. But you can also argue it another way. When this thing's level, the rope is holding none of this guy's weight. All of the weight is being held by, all the FG rather, is being held by the scale. As this increases, this guy's going to pull more and more and more on the rope. And what that means is he's going to actually be pushing less and less and less on the scale. To the point when this thing is straight up and down, he's just going to be hanging fully from the rope and the scale's not going to be necessarily measuring anything. So you can think of it that way too. There's this interpretation of it, or you can think of it as the incline increases, the rope holds more weight, and the scale holds less. And we can see that, well, what's the rope holding here? Let's continue the free body diagram. We've got the rope going up this way. We'll call that F tension in that rope there. Well, what is this thing going to be equal to? This guy's not moving here, and so we have to have forces that are balancing out any potential accelerations. Fn and Fg perpendicular are balancing each other. F tension has to be balanced by some other force parallel to the incline, and we have a force that does that right there. So if this were totally level, this FG parallel would be 0. But as the angle increases, this is going to get longer and longer and longer and longer. So we can see that the tension in the rope must be increasing with every little bit of incline. So the tension in the rope here, if we look at example 2, as the angle of the ramp angle increases, what happens to the tension in the rope? It has to increase. You can argue it. The tension must increase as the rope holds more and more weight. So it's this trade-off here between the scale and the rope compensating for the FG on this guy. Flip the page. So here's the general picture of what we're going to be looking at here. What the previous example shows is that for the objects on a ramp, the force of gravity pulls the object down the ramp partially. I broke this up into components earlier. This guy here is FG. Now, the book is going to call it a squeeze component and a slide component. I don't like that language. I will acknowledge that it exists because that's another way to think about it. If that's an easier way for you to wrap your head around that, that's great. I will use alternative language. We call it the squeeze component because it's this component here that holds the object to the ramp. And the slide component is called the slide component because this causes the object to slide down the ramp. Now, I said earlier that components always meet at 90 degrees. That's just what components do. So I'm going to label these here the way I labeled them before. So this squeeze component is what I call FG perpendicular, and this slide component is what I call FG parallel. And I made the argument before, but I could, again, if you want to see it, come talk to me about it. But this angle here and this angle here are going to be the same. So we can see what this is going to look like. We've got a 90-degree angle here, and we've got an angle here. in the problems that we look at, we're going to know what that value is, but right now we don't. But we can talk about what it is in general. In general, FG perpendicular is going to equal, this is the hypotenuse, so that's going to be big FG. And this is adjacent to that angle. So adjacent is cosine. It's going to be FG cos theta, which means FG parallel is going to be FG sine theta. Let's continue with the free body diagram, shall we? Fn is always parallel to the surface. So it's going to go up at an angle like this. Well, Fn perpendicular to the surface is going to have to equal out the component of gravity that's also perpendicular to the surface. That's this guy here. So Fn is going to equal Fg perpendicular, which we know already is equal to Fg cos theta. And this is the force scenario that we've got going on here. This parallel component, also called the slide component by some, is what causes this object to slide down the ramp, while it's this squeeze component here that's causing, that's countering the Fn, and this is actually what's causing these two together are causing the friction to occur, whatever friction exists between these two surfaces. So let's flip the page. And you know what? Let's flip. Oh, should I do this? This is the argument. All right, I'll go through this real quick here. You can skip it if it's doesn't. Yeah, if you don't like it, or if it doesn't, it's not necessary to make sense for you. But this is the argument for why those two angles there are the same. Why this angle here, this big angle here, that is angle 5, and I'm going to prove to you that that's equal to angle theta. So angle 1 is 90 degrees. Well, why is that? Because FG is straight down and perpendicular to the bottom, the flat surface on the bottom. It's just the way gravity is straight down. So if that's 90, then this guy here is going to be 2 is going to be 90 minus theta, because angles in a triangle add to 180 degrees. So 180 minus 90 minus theta equals 90 minus theta. Angle 3 is going to equal angle 2, which equals 90 minus theta. Opposite angles are equal. If you took a look at the supplemental angle stuff that I did with you. Angle 4 is also going to be 90 degrees. Because this is an FG, because FG perpendicular is called that because it is perpendicular to the incline. So then angle 5, angles in a triangle add up to 180 degrees. So angle 5 is then going to equal 180 minus 90 minus 90 minus theta. If I take a look at what's going on here, that's, and I distribute that minus sign in there properly, that's going to be equal to 180 minus 90 plus theta. Boom, boom, boom. That equals theta. So we can see that that angle there and angle 5, or the big line that I've drawn there, are actually equal to each other. That's the geometric way to prove that. Flip the page. We'll do a couple examples, and then you can practice some of this stuff here. Here we go. Example 6. We're going to do 2 examples, one without friction and one with friction. So we're going to consider a 2 kilogram mass sliding down a frictionless 25 degree ramp. So that's important information here. Frictionless is important. We want to go through this. These are the steps we want to go through here. We want to draw a force diagram. Then we want to draw the gravity component triangle. We want to find this amount of squeeze and slide components, or the values for the 2 different components of gravity. We're going to find the normal force, and then we're going to find the acceleration due to gravity. So the free body diagram just has the actual forces that act on it, not including the components. So the free body diagram is going to look like this. Fg, I should put it here. Fg is straight down from the center of the object. Fn is perpendicular to the surface out from the center of the object. That is the free body diagram. That's it. Now, so force diagram, check. Now we want to draw the components of gravity. Now the components have to be perpendicular to each other. And one of them, the first one I'm going to draw is going to be perpendicular to the surface. It's going to be the same as Fn. And those got to be perpendicular there. Now, I've had a lot of students ask me in the past, even some of you have asked me this year already, do you care? Do I have to be good at drawing? What if it's like, what if I can't draw? Okay, well, if you can't learn this, you can learn this. You can learn to draw lines that look perpendicular to each other. This is going to be very important for you to figure out. The 2 components need to be perpendicular to each other. One of them's got to be perpendicular to the incline. So draw the perpendicular incline first. It's going to cut straight through it nicely. And then you want to draw it as long as it needs to be, so that a perpendicular line can be drawn to Fg. You don't have to be an artist to be able to figure that out. It's really important that you get these lines drawn properly. So if you have to practice that, practice that. Okay? So this guy here, the way I've labeled it, the book labels them squeeze and slide components. I'm going to continue to label them Fg perpendicular and Fg parallel. This angle in here is 25 degrees. So we know here, there's the component triangle. Now we're going to start putting some values in there. We know Fg is 2. Let's take a step back. Fg equals mg. M is 2. G is 9.8. So 2 times 9.8 is 19.6 newtons. We know that Fg perpendicular is equal to Fg cos theta. So that's going to equal 19.6 cos 25, which is going to equal 17.76. And Fg parallel is going to equal Fg sine theta equals 19.6 sine 25. That's going to equal 8.28 newtons. Cool. We've got the components. The normal force is equal to and opposite this perpendicular component. So Fn is going to equal Fg perpendicular, which is going to equal 17.76 newtons. And so now we can actually go find the acceleration of the object. It's all going to start with F net equals ma. So what force, now you have to ask yourself, what forces, I'm going to write this down, act in the direction of motion? Okay, that's what you have to ask yourself. In this case, the only force or piece of force that acts in the direction of motion, i.e. this block is going to slide down the ramp, is this parallel component here. So in my F net equals ma equation, it's going to be Fg parallel. That is the only force acting in the direction of motion, and that's going to be what's causing my acceleration. It's going to equal MA. I can put some values in here. So I'm going to get 8.28 is going to equal 2A. So A is going to equal 4.14 meters per second squared. And we need a direction because acceleration is a vector. And in this case, the direction that makes the most sense is relative to the ramp. The direction here is going to be down the ramp. Put a box around this. That's what you got to ask yourself every time. That's it. That's all that's going on. The only addition here that is new from what you were looking at last year, or even what we've looked at in the review already here, is this breaking things up into components. One more example. Oh, yeah. Then there was one thing I missed in the previous diagram. I'll re-add that to this one here. So, this is not how you're going to be given the instructions. Here's what the instructions are actually going to look like on a test or a quiz or your final exam. They will say, consider a 5 kilogram mass sliding down a rough mu equals 0.2 35-degree ramp. Find the acceleration of the mass. That's all it will say. It might even go further, but we haven't got there yet when we look at energy and momentum. But this is what it will say. So now we got to add forces here. There's a few pieces of information that are important to recognize here. We know that this thing is sliding down a rough ramp. That tells us there's going to be friction, and it tells us the direction this object is moving in, which is going to tell us which way friction is acting. So we're going to draw our free body diagram here. From the approximate center of the object, I'm going to have FG. I'm going to have FN perpendicular to my surface. And now we're told this object is sliding down the ramp. Friction opposes motion. Force of friction goes up that way. There's my free body diagram. Now, I'm going to break these things up into components. I'm going to use green for that. The other thing that I didn't include on the previous diagram that I should include on this one is what direction, that I'm going to include on this one, is what direction we want positive to be. So on this previous one, we said the assumption that I made, the way the math fell down, is that this direction was positive, and that's because we know the object is accelerating down the ramp, and I ended with a positive value. So my assumption that I didn't make clear was that down the ramp was positive. And so that's what, because this object is sliding down this ramp, I'm going to call that positive as well. Okay, so we're going to break this guy up into components. I'm not going to use green anymore. I'm going to use red for these green. The other thing, we've got our perpendicular component, and we've got our parallel component. These two meet at a 90-degree angle. So this angle here is 35 degrees. This is FG perpendicular. This is going to be FG parallel. So the blue is my free body diagram. The red now I've added are the components. Let's find some values here. We know that FG is equal to 5 times 9.8. So that's going to be 49 newtons. So this parallel component is going to equal 49 sine 35. And my perpendicular component is going to equal 49 cos 35. So 49 sine 35 is 28.11. And the perpendicular component is going to be 40.10. Sorry, 40.12. I know writing to the left is kind of tricky, but you can do it. I believe in you. This perpendicular component is going to be equal to Fn. Fn equals Fg perpendicular, so that's going to also equal 40.12 newtons. And we need that Fn because we know that the force of friction is equal to mu Fn. And now we've got friction because we have a value for mu. So the force of friction is going to equal 0.2 times 40.12. So that's going to equal 8.02 newtons. So now I can go through and I can find the acceleration because I've got all my forces. We've got F net equals ma. I'm not going to write the question out this time, but we're going to ask it again. What forces are acting in the plane or in the direction of motion. Now, the direction of motion is this way. It's up and down the ramp. So there's two pieces or forces, individual forces, that are acting in this direction. One of them is friction. The other one is this component here. Okay? So we've already said that down the ramp is positive. FG parallel is down the ramp. So we're going to have FG parallel, and friction is acting up the ramp, so that's going to be minus our force of friction, and that's going to equal MA. So FG parallel is 28.11 minus 8.02 equals the mass of our block times its acceleration. So we're going to see here the acceleration is going to be equal to 4.02 meters per second squared, and we can see that because, and this value is positive, we said down the ramp was positive, and so this block is accelerating down the ramp. We're done. Okay. I think this is relatively straightforward. This shouldn't be overly difficult. There is one more example I'm gonna show you, but I'm not gonna do it. It's gonna be part of your homework. It's this guy here. We've got a 6 kilogram mass sliding up a rough 45-degree ramp with an initial speed of this. This is how you'll be asked the question. You won't be given A, B, C, or D. Okay? This is not how, all of this, I'm not going to scribble it out now because I'm not going to go through the example with you. This will not be present on a test. The only instructions you will be given will be to find the acceleration of the mass. Maybe E might not even be given. The only thing that might be present is find the time to stop. That might be it, and you would be expected to do it all. So it's going to start the same way. You'll have your free body diagrams, put in gravity, put in the normal force, break up gravity into its components, find the value for the parallel and perpendicular components, find the normal force of the mass, which is going to be equal to and opposite the perpendicular component of gravity, find the force of friction on the mass, which is going to be equal to mu Fn. The important thing to recognize, though, is which way is friction acting. Ask yourself that as you go down this. We're told the object is moving up the ramp. Okay? So label friction on here appropriately. Label a direction that you want to call positive, and then everything needs to be consistent from that. Find the acceleration of the mass using F net equals ma. Find the time to stop using kinematics. Okay. So I want you to try this for homework, as well as flip the page. You got some more questions here. You are going to be trying, I want you to do 3. I want you to do 5. I want you to do 9, 11, and 12. That plus example 8 is going to be your homework from this lesson. As always, if you've got questions, please ask. The questions, though, don't just say, I need help with this number. I need you to ask me specific things. I don't understand this about this question. I'm stuck here. I want to see what you've done. I want to see, so don't erase your work if you're coming for help. You've got to give me more than, I don't get this question. Just tell me what about that question you don't get. Otherwise, I can't help you. I'm not just going to crank out solutions to every question for you guys. So please be specific when you're asking for help. I am happy to give help, but you've got to do more than, I don't get it. You have to tell me specifically what you don't understand. As always, feel free to come for help. Good luck. May the force be with you.